Hello students, in this video we'll discuss about the applications of finite automata and properties of regular sets, especially the decidable properties. And we have closure properties also that we will discuss in the next video. So in the previous video we have discussed about how to convert a regular expression to finite automata and a finite automata to regular expression. So we have discussed about state elimination methods and state creation methods for regular expression to finite automata. So first we'll go with the applications. Why we have to study this subject, where it is going to be used. The first, finite automata. So then these are some applications listed out here, like lexical analysis in compiler. So in compiler design we are going to have the 7 phases. The first phase of the compiler is lexical analysis. Like the rules of lexical analysis are going to be specified with the regular expressions. So that we'll discuss in the next slide. Then string matching algorithm, like might be you are searching somewhere, you have typed some keywords, and if you want to retrieve all the files which contains that, then you can go for the substring algorithm, right? Like construction of automata for substring. For example, if you want to search which starts with some string, then go for the starts with some string like compiler in automata. Then you can just convert the program diagram into the table, then you can write the program, and it's very easy if you are representing the things with the finite automata. Network protocol analysis, like how the data is moving from one router to another router, right, or one node to another node. You can represent as the nodes and the flow, the cost, and you can see that what will be happen if it is broken or something. And of course very large scale, right, integrations, VLSI designing also will use it, like short circuit or in circuit design. For example, you are at one state, and if the some signal is given here, then where should I go, right? So in that case also we'll use this finite automata. And of course, natural language processing, NLP, and this is the most advanced application of finite automata where we are using, like for example, it's you are dealing with robot or something, right? Then you have started with some word, what is the next word, and predicting it. That can be done with the finite automata. And DNA sequence analysis, like which is matching our ends with a substring, like using such, then we can check whether this DNA is matching with other person DNA or not, and what is its pattern. Okay, that. And of course digital circuit design, like traffic signals, the person is waiting at the traffic signal and the signal is waiting, and if the signal is yellow, where it should go must be in the waiting, and if it is green, then it should change its state from waiting to running, and if it is red, and it should change from waiting to stop or about, like. And while he is running, if the signal is green, keep on moving. If it is yellow, just wait, and if it is red, about, stop, like. We can use this automata and robotics, pattern recognition. So there are n number of applications of this finite automata. So out of these we'll discuss few. I can say that 2 or 3 in the slides, and we'll go to the properties. So the first and the foremost one is, the most important one is of course the real time, right? What we are going to study, especially real time means, in of course in the market we use all, but we will study in the next semester, okay, or sixth semester you'll be having a like compiler design. There you have to specify this. Again you are going to study this regular expressions again in the compiler design. So the first step is lexical analysis. Like you take the C language, what are the tokens in the C language? For example, if you are developing your own programming language, you must specify what are the rules of identifiers and what are the keywords you are going to have in your program, right? And what are the rules for the digits, numbers, floating point numbers, what are the rules? So for example, you are saying that in C language it starts with a underscore or letter. So starts with letter or underscore followed by any number of letters or digits, whole star. See, First rule. Okay. Or in Java, the identifier rules have been changed and they have even starts with the dollar. Then you can write it letter or underscore or dollar followed by letter or digit all star. That's their wish. If you are writing your own programming language and you want to give that, why don't we add our rupee symbol? That's my wish. Dollar or rupee symbol. If your keyboard is having this, you could add it. So like numbers. So digit followed by any number of digits. After dot, how many digits you are expecting? You are expecting one digit, or two, or three, or four. That you have to specify because infinite number of symbols are not allowed after the floating point, right? So that you have to specify here. Okay. So how to write it? Keyword then only. Variable name starts with capital letters or small letters followed by. I think they have not even mentioned the other symbols. Like that, you can do it. So string matching, of course, it is nothing but pattern string with a. Okay, you can construct DFA that ends with so that it would be very easy to search in your documents while you are googling or while you are searching somewhere, and even your current folder also. Okay, in your system, so you can use it. Then the gaming application. For example, you might be playing some games at home, right? The ping pong ball. So if it is starting from somewhere, then going here and going from here, the states. If it goes to this state, what we have to do? If it goes to this state, what we have to do? Like it's a simple states, the possibilities. Okay. Then for example here, flee, escape, and roam, find peasant, chase, get close, fight, and get far, lose light off, go to room again. Then if you find a dragon, just flee away. It's how the boat, the computer generated character in a video game, how it is going to work. So it's having three states: flee, roam. The first one starting state is roam. If it finds a dragon, it flew away, right? If it escaped from the dragon, again it will start roaming it. If you find a peasant, then chase, get close, fight to the dragon, fight with the dragon. Okay, fight, get far away if you are losing a sight, right? Then again go on roaming. Okay. So like that, you have to specify the behavior of the bot in the game with the machine. So that's called finite automata. Right? So let me go with the properties of regular sets. See guys, we are going to have the two properties. One is decidable properties. Okay. Another one, closure properties. Closure properties. So let me tell you something before starting the concept of decidable properties especially. See, if you're saying that something is decidable or not in the regular sets, yes, every property is decidable under regular. I'm going to say that. Can you say that the language accepted by the finite automata is finite? Yes, it is decidable. We can say, right? Or infinite, we can say. I gave you some rules, I'll tell you that before starting it. Every problem is decidable under regular and every property is closed under regular. The closure properties we'll discuss in the next video. At the time I'll tell you again. What does it mean by disjoint sets? See, assume that we are having two machines, right? M1 and M2. We're having two machines with some automata. Assume that we are having some states and all. Okay. Is that problem the language accepted by the M1 intersection language accepted by the M2? Is it common symbol or not? Of course, we can simply tell it. Okay. Simply we can tell that if there are no strings accepted in both the machines, right, common strings, we can tell it. And same way, how can you say that whether a language is accepted by the machine is finite? Sorry, empty. No string should get accepted. For example, you are giving in a machine, and how can you say that the language accepted by this machine is empty without looking at the finite automata? Logic is very simple. If there is no final state, if you want to say that some string is accepted, assume that there is no final state. You have taken automata like this: Q0, Q1, Q2, Q3. We have some states like A, B, A, B, A, B, something like this. Assume that. If this is a final state, I can say that A is accepted, BB is accepted, BAB accepted, BAAB. If there is no final state, nothing is going to be accepted, right? Or if you have a final state, but from the starting state you cannot reach it. In that case also, the language accepted by the finite automata is empty. We can tell it. So it is decidable. Universal, the simply reverse of the emptiness means no string should get rejected. Universality means it should accept the universal language, means no string should get rejected, means every state must be a final state. Every state. Then only we can say that it is universal. Or if you are having a non-final state, that should be unreachable from the starting state, so that epsilon accepted only A, only B, like it's just reverse of the emptiness. Here no final states or all final states are unreachable. Here no non-final states are all same, reverse of it. Membership. Can you say that a string is accepted by the finite automata or not? Of course, yes. From the starting state, if it reaches the final state, accepted. Otherwise, not accepted. It's not a big deal, right? Then finiteness. See guys, for example, I'm having a state like this: A, B, Q1, A. See, what are the strings accepted here? A, B, A. That's it. Only two strings. Only two strings. Because there is no loops and everything. Self loop. For example, if I'm having like this: A, B, A, B, B, A, B, 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 A. Like how many? I cannot take any number. So when you can say that it is finite, there should not be any cycles or loops like this. Then it is finite. If it exists, then infiniteness. Now can I say that two machines are equal? So the language accepted by one machine is equivalent to the language accepted by the other machine. Then we can say that those two are equal machines, right? So this is about, of course, every property, if it is listed out here or not listed out here, every property is decidable under the regular languages. So if you are given two machines and you are asked to check whether they are equal or not, so try to take a string which is accepted here, not there. You can tell it. For example, you have a machine here, okay, and you have a machine here. Assume that we are having 4 states and assume that we are having 3 states. Then you can take what is the minimal one, 3 states, right? So take the 0 length strings, 1 length string, 2 length strings, and 3 lengths. Not even 3 guys, you take 2 length, that's it. If it is minimum, take -1. If all are accepted here and here, yes, they are equal. Otherwise, not equal. You can simply tell it. Okay. If the minimum number of states are 3 states, for example, if it is M and this is N states, and if M is less than N or M is greater than N, what is the minimum? So identify the min of M comma N. If min of M comma N is N, then you take all the strings of length N or N minus 1, it's better. If all are accepting here and here, that is accepted, otherwise not. In exam, if you are given such questions, you take some strings and you tell that yes, accepted, accepted, not accepted, accepted. Okay, good. If something is accepted here, not equal. If something is not accepted here, but here, not equal. If everything is accepted here and here, both are equal. But where should I take? If both are infinite, can't I go to the, can I go to the infinite number? No guys, it's very simple that if you're having minimum number of states, take the strings until that length, that's it. Until, not even till, until that length. If all are accepting, well and good, otherwise not equal. So this is how it is going to be. So in the next video, we'll discuss about pumping lemma and its closure properties.